It's 27th. Okay. Quick recap of what we have seen last time. Yeah, tell me. Yeah, so we have introduced one more method for reduction of Boolean expressions. That was known as a tabular method or Quine-McCluskey method. Okay, there were certain steps. Okay, the procedure was quite different from what we have seen for the K-map, but the fundamental principles behind those reduction techniques remains the same. We are using the axioms of Boolean algebra so as to get as minimum expression as possible, so that the cost would be minimum, and hence this it would be much faster, it would be much smaller, it would be much simpler circuit, and it would implement the same function which would otherwise would have been not possible, okay, if we wouldn't have used this reduction methods, right? Now let's go ahead, let's take some some important circuits, some widely used circuits. The first of it is, no, let me first introduce the adder. Okay, we have already introduced the full adder. Okay, so can you tell me, I just want to just revise it, a full adder. Yeah, so how is a full adder, you tell me? A full adder, what is full adder? What is a full adder? Which adds 2 bits along with a carry, right? A half adder is where we don't have a carry, previous carry is not there. So let's say a 2, let it be A, B, and this, let it be previous carry, so this, let it be I minus 1. Alright, so we got the truth table of sum, okay, sum and carry at that instance. Okay, the I indicates that moment, okay, or that bit calculation, the bit under consideration, and I minus 1 indicates the previous calculations. So let me write them, all the combinations. We have seen this, but no, there's something which I forgot to take. Yeah. Tell me, what is this? 0, 1, 1, 0, carry here, 1, 1, 1, 1, right? So any procedure or any method for designing, or the procedure for designing is the same, will be the same. Okay, what is the procedure? What would be the procedure? Given certain specifications, if certain specifications are given, okay, say for example our specifications were where we simply need to add this, right? A plus B, that's what we need to add. Now the procedure remains the same. We draw the truth table, we take function by function, take this function, another function, draw K-map for each and every function, minimize it, okay, as small as possible, and then realize it. So if you draw the K-map for this, this we have already seen, okay, A, B, C, I minus 1, so let it be 0, 0, 0, 1, so it will be 1, 1, like this, right? 0, 1, 1, 0, 0, 1, 1, 0, and so on. So this is for the sum, right? So sum was, so what are the expressions for this? We got it as A, no, XOR of B of XOR with C. Is that okay? C of I minus 1, right? So just remember that. Then for the carry, we got some expression, right? What was that? Turn your pages, tell me the expression. BCI minus 1. 0001111, something like that. Yeah, tell me. Now, yeah, we can calculate it here. You tell me this way, like this, and like that. Okay. Now, instead of combining this, now this will give me some expression. Ci. Okay, it will give me some expression. What is that? A Ci minus 1, or no, this one B Ci minus 1, or what is this? A B. Okay. So instead of this, I want to represent it with some different, some different expression. Okay. Let me for time being. Okay. I want to simply, encircle these individual ones. Okay. Let's instead of encircling it, I will say that instead of using K map, I will simply write these expressions directly. So this, and this. So what are those expressions? So this can be, or can be represented as Ci equals, you tell me, this one is A bar BC, right? So A bar B Ci minus 1, or the other one A B bar C, A B bar Ci minus 1, and or this one, right? A B C bar, right? That is I minus 1, and yeah, A B Ci minus 1. Now you simply realize this. Okay, express this in some different form. So Ci would be, this. Okay, if I group this, if I simply take Ci minus 1 common, it would be, the A XOR B XOR B multiplied by Ci minus 1. Is that okay? And other one, or AB So it will be AB, right? Simply AB, because C into Ci minus 1 will go off. So just look at this expression and this one. So I'm trying to minimize the things now. Okay. So let us represent something with this A. Now first of all, let me give some labels to them. I am labeling this, okay, A XOR B as what is called as a P at some stage I, the current P, let's say, and this as G, AB as G, GI. I'm simply labeling them, okay, that's for a reason. Now what I'm saying is, let's see what we are doing right now. So let's take this full adder circuit as a black box. Okay, so this is a full adder. Let's say it's a 0th bit. Let's take a 2-bit full adders. Okay, 2-bit. I mean, I'm implementing 2-bit addition using 2 full bit adders. So what will I require? This A, right? A0 and B0. I mean the 0th bit of both the numbers, and the previous carry, if any. Okay, usually that is 0. Ci minus 1. So let it be C minus 1, and it will give me the sum and the carry, right? So it will be sum 0, and the carry will be given to the next bit, right? Which will again take an input as A1, B1, full adder, that is 1, and it will give me a sum of S1 and a carry, right? So this is C0 and C1. Like that it will go on, okay, until number of bits you require. So if you want to implement 2-bit addition, go for 2 such full adders, 3-bit addition and so on. N-bit addition you will require N such full adders and so on. Now the problem here is, see here, the sum expression. What is the sum expression that you get? The sum expression is A naught XOR with B naught and XOR with C minus 1, right? Once you do that, the carry is again, the sum is generated, the carry is generated, and then this have to wait until this carry comes, right? So this is like a serial processing which is happening here. Although at the same moment they both have A1 B1, A0 B0, both of them are having the inputs with them. This fellow can't calculate this S1 and C1 unless and until this C0 arrives at the at the input of this FA1, right? That means it has to wait until this carry of the previous stage is generated, right? So say for example it is a large large number of bit addition, say for example 32-bit or 64-bit, and and the processing speed is very high. So we are very concerned about this carry propagation delay, what is called as, okay? So the delay which is required to propagate this carry from one stage to the another is called as carry propagation delay, okay? What the delay says, okay, what this can cause, the further stages can't calculate the sum and the carry unless and otherwise the carry from the previous stage is arrived. To solve this problem, okay, we come up with a circuit is proposed, is called as carry look ahead adder. Carry look ahead circuit is proposed. Look ahead. So that is what we are going to see here now. For that purpose, what we have seen is a full adder is there. A full adder expression, I am simply representing it with So what was the full adder expression? Can you tell me now? Now I am giving an index I. So Si indicates for the 0th bit or first bit, I mean it indicates the index of the bit number, right? So Si, what was the expression, you tell me? Some expression. What was that? A XOR B, right? AI BI, right? So I will write it as P, that I have represented by P, right? So that is PI, that XOR with C of I minus 1. Is that okay? What is carry? Carry, tell me the expression. GI multiplied with C I minus 1 or with, you know the expression, right? So see here, this one, okay? So Pi into, so GI plus Pi into Ci minus 1, right? So let me grab this. So GI plus Pi into Ci minus 1. Is that okay? Now we don't consider, we don't bother about this, because see, this sum is also dependent on the carry, okay, and the carry which is being generated at this stage is also dependent on the carry of the previous stage. So let's concentrate on this expression, okay? So let's take for I equal to 0. What is that? So it was C0 G0 plus, because see, for this circuit, okay, for FA1, A1 and B1 are already there. What is not there is C0, okay, and it will go on. So let's control on carry. C0 is G0 plus P0C minus 1. Now C minus 1 is already there, okay. What is there with us here? B1, A1 and C minus 1, but we don't have C0, right? Similarly, I equal to 1, you take what we have, C1 G0 G1 plus P1 times C0, right? So I can write it as Z1 plus P1 times now G0. Is that okay? Plus P1 P0 times Ci minus 1. Can you see what is happening here? I have not predicted, I have accurately calculated this carry way ahead of the calculations of this, the lowest low bit, okay? See, we here are no more dependent on C0. See here, the C1 is no more dependent on C0. It is directly dependent on C minus 1, isn't it? That means we are looking ahead of this carry. Okay, I mean this delay is saved. Okay, so if we go on for, let's say, I equal to 2, I equals to 2, you take, what is the expression? C2 bolo, G2 plus P2 C1. So can I represent it with like this? G2 plus, now P2 is, now P2 we already have. What is P2? G2 and P2, what are those? Simply the XOR of this, right? P2 is simply XOR of this, G2 is simply AND of them, isn't it? So P2 C1, what is that? Now you represent G1 plus P2 P1 G0 plus P2 P1 P0 C minus 1. Can you see anywhere the carry dependence on just the previous stage? C2 का carry है, मतलब इसके आगे अगर और एक कुछ bit होता, let me draw that. Simple, no? I mean we have simply look ahead of the carry operation. So what is the carry generated here? C1, right? So what are the bits required for full addition? A2, B2, isn't it? The carry generated is C2 and sum generated is S2. This is full adder 2, and it will go on. So what we are simply saving this propagation delay. Okay, now at a time this say for example, let's consider this FA1. FA1 don't have to wait till C0 is C0 is calculated. This C0, okay, where this C0 is directly dependent on C minus 1 and so on. Okay, so this kind of adder is called as carry look ahead adder or carry look ahead circuit. Okay, this is being widely used in the digital electronics. What is the overhead required here? Now you can see the number of gates, right? The number of hardware, the hardware cost is increased here. Okay, so there is a trade-off. If you want fast calculations, okay, fast arithmetic, you add some more hardware. Now there may be trade-off that it may not be always possible to reduce the time by putting on more and more hardware. It may happen that the hardware delay itself may be so much that the carry look ahead वाला जो delay है, like carry propagation जो delay है, वो may be that delay may be much less as compared to this hardware delay. So it may happen. So there is a trade-off. Okay, are you getting what I'm saying? So we don't have to know the adder is no more dependent on the carry being generated by the previous. It doesn't have to wait for that. Okay, so this kind of circuit is called as carry propagation adder. Okay, so the homework for you is to look away such kind of possibility for full subtractor also. Okay, the subtractor circuit, right? What is full subtractor? Now you can similarly define the circuit for full subtractor. What is subtractor? You tell me a bit. Half subtractor, we have already seen that, right? Half subtractor we have seen. Half subtractor, have you seen that? No, okay. Adder is the subtractor. Can you tell me subtraction operation we have seen it? Okay, don't tell me. Subtraction operation we have seen. So similar to half adder, we also have a half subtractor. In half subtractor again you go by the same way. Yeah, homework for you is to realize this complete circuit. Okay, just note my words. What I am saying is you need to realize this complete circuit. Say for 2-bit adder, 3-bit adder, you start with 2-bit. Okay, then go for 3-bit, 4-bit and so on. You will get a big circuit. Okay, this big circuit, why it is generating? Because this P0 and Z0 themselves are represented as XOR and AND operation of the original bits. So challenge for you, not a challenge, but that's a homework for you, is to realize it. Okay, realize complete circuit. In realization, what do you mean by that is, at the end just tell me what is there inside this box. Input to that box will be the number of bits. Let me draw it with a minimum possible way. So this is a sum and this is a carry. some carry, and let this be, x be, let's say 2-bit, and this y also be 2-bit. Say for example, you may take 3-bit, 4-bit, just realize it for 2-bit for time being. Okay, see how how the circuit would look like, and compare that with the the circuit with no carry look ahead, this operation. Okay, are you getting what I'm saying? So just realize this circuit without carry look ahead circuit and with carry look ahead algorithm. Okay, do that. So what is there inside this? You need to find it out. I mean, we have realized the expression, you just need to draw it. Alright. For half subtractor, same, okay, we again have a 2-bit A, B, and the output we have. Now you tell me, for subtractor we have the difference and the borrow. 0, 0. So the difference, you tell me, 0, 0, 0, 1 ka difference, 1 with a borrow, 1, 0, 1, 1, and so on. Is that okay? Half subtractor. What about full subtractor? Now the procedure remains the same. Okay, you realize the circuit for D, realize the circuit for B. Okay, draw the K map, nicely realize the expressions, and you'll get the circuit. Okay, procedure remains the same. What about full subtractor? What about full subtractor? Compare that with the full adder. What is full subtractor? Borrow from the previous bit, right? We need to consider that also. So A, B, and no, I should not say B, but let the borrow or the carry, let it be the same, because this borrow, we don't really go for subtraction. We make 2's complement of the, what is that, subtrahend, and then do the addition, you know that. And then the difference and the borrow of new stage, let it be Cn or I minus 1 and I. Tell me, 0, 0, 0, 1, 2, 3, 4, 5, 6, and 7. So all the possibilities are covered. Tell me borrow operation for this. What is the difference of A and B? 0. What is the result? Now how do we calculate? How do we incur the third bit? Whatever the result is there for the A and B, okay, you use that and subtract this Ci from that result. Okay, Ci minus 1 from that result. What is that? 0 and same procedure here. 0 minus 0 is 0. You subtract this 1 from that result. Okay, the previous result. What is that? So 0 minus 1. Difference is 1. Borrow is 1. Again you tell me 0 minus 1. Okay, 1 with a borrow. Okay, but no, let me write the borrow, and the result was 1, right? So 1 minus 0 is 1 again. Is that okay? Yeah, here. Yes. What about this? 1, 0. Here 1 minus 0 is 1 there. Okay, 1 minus 1 is 0, so both will be 0. What about this? Right? What about this? 1 minus 1 is 0, 0 minus 1 is 1 with a carry, so it will be like that. Is that okay? Anyone who didn't get this? So procedure again remains the same. Realize the function for D, realize the function for C, that is the previous borrow, and look for a possibility to have a carry, not a borrow look ahead subtract. Can we have that? Okay, so homework for you is to realize this, okay, with and without carry look ahead subtract. Just look for that possibility. Is that okay? Let's move ahead. Alright, so so far we have seen very basic things, okay, very basic things, like we have realized some some expressions of Boolean expression. We have seen a few design problems, okay, and we have seen how they can be minimized and so on. There are some standard modules which are present in when you go for realization, actual realization. You don't go for pen and paper method. You realize it with various hardware description languages which are available. the computer. So this hardware description languages or this software is already having a predefined modules in them. Okay. Remember, you last time I've given you an homework saying that design a circuit so that it would be your cell phone would be able to transfer or receive a data from two different sources. You remember that homework? So say for example you need to design a circuit such that you need to receive the data from two different sources. Okay. With an enable switch, okay, with a selection switch. Say for example, if selection switch is not it's 0, you take the data from one person. If it is 1, you take the data from the another person. Okay, so this is what I meant. Okay, so if there are two cell phones, both of them, if you need to receive the data from both of them, okay, you can't receive at a time. Okay, either you need to select this or that. Say for example, this is a Hindi song or this is a Telugu song there. If you need to receive, okay, you need to first say that from what you need to receive at that time instance. So here it will say that, okay, let it be for 0, it will receive from Hindi, it will receive a Hindi song. Let it be for 1, it will be receiving Telugu song, and so on. So such kind of operation, okay, is called, how can you represent that operation as with a simple circuit? So simply we can represent this with an AND, okay, and okay, let me realize that. Okay, let me realize that first. So this H and T, okay, they are binary variables, and let this be a mobile phone which is receiving that data. This may be 0 1, okay, 0 0 both, 0 1, 1 0, 1 1. All 4 possibilities are there. I mean, this data being 0, it may be 1 here, it may be 0 1 here, it may be 0 here, and so on. Okay. When it is 0, I am saying that I will be receiving, now there is a selection switch there. Okay, let me put a selection switch there. The selection switch, let it be S. Okay, now I have, for selection switch to be 0, it has this many possibilities. Okay, isn't it? For selection switch 1, again we have this 4 possibilities: 0 0 0 1 1 0 1 1. That means what? If I am putting this selection switch as 0, whatever the data it may vary, it should receive from the H. If I put a selection switch as 1, whatever the variation is there among these, I should be able to select this, T, isn't it? So there are 8 such combinations which are happening here. So we cannot draw this line; it will create some confusion. So 0 0 1 and so on. What I am saying is, when selection switch is 0, okay, you receive the data from H, right? So H will be simply replicated there. So 0 0 1 1. Is that okay? When it is 1, it will simply copy this. Yeah, it will be 0 1 here. It will be 0 1 0, isn't it? So if you realize this with K-map, so 0 0 0 1 1 1 1 0, you tell me values for this, you tell me. This is S, H and T, right? So if selection switch is 0, it will 0 0 1 1, so it is simply 0 0 1 1, and it is 0 1 0 1 10. Is that okay? So I can group this, group that, just because there are no isolated ones, and this may be the the minimal possible expression. What is the expression for this? You tell me. S bar H, is that okay? And what is this? S T. Simple, right? So the function M can be realized as S bar H and S. Is that okay? Okay. How simple this is? When it is 0, you receive the data from H. When it is 0, you receive the data from H. When it is 1, you receive the data from T. Simple one. So what is the crux of this? Now this kind of circuit is called as a multiplex. Okay, when you need to receive a data from multiple lines, okay, then you need to give a selection. Say, now let me define that. A multiplexer is a circuit, okay, which has 2 to the power n inputs and n selection lines. This is a multiplexer this circuit is there everywhere. Okay, almost all of the digital electronics have this circuit where you need to deal with multiple datas. Okay, when there is problem of selection, then we have to use this circuit to the power n inputs and n selection lies. What it will do is it will simply redirect. Okay, redirect or directs or directs the data from the selected input line to the output. There is only one output, isn't it? So there are 2 to the power n inputs, n selection lines, and one output, right? Is that okay? Now, see, what is the crux here? What is the crux here? The crux is this AND gate. Isn't it? If you realize that, okay, what is that? Okay, so this is X. Now let me from Hindi, and this is for Telugu one. So this is bar, no? So it will be, let this be S and a bar of that, right? So let me put an inverter there. Simple circuit. So here okay, so OR of this, isn't it? Require an OR gate also. Isn't it this realization, is it okay? H S bar that will give you H, and this one S T will give you Telugu one, right? So this is the M function which we have in this. What is the crux here? The crux is this AND gate, isn't it? The AND gate is having this functionality. The output is, so just concentrate here. What is that? This 2. When you give 1, it will simply transfer this data here, isn't it? That means what? You make one of the input of the AND gate as 1. Okay, the other will be simply transferred to the output. If it is 0, then output will be 0. Okay, same thing is happening here, isn't it? So this kind of circuit is called as a multiplexer circuit. Okay. Can you draw a circuit for this is now what is that? The 2 inputs are being selected, right? So we require only one selection switch. Say for example, there are 4 inputs which are required. Require 2 selection lines, isn't it? I mean, this is 2 to the power n inputs and n selection lines, isn't it? So inputs there were 2. That means n was 1. So one selection line was required. Can you quickly draw a circuit for 4 inputs and 4 input multiplexer, 4:1 multiplexer. Now this is called as a 2 to the power n is to 1 multiplexer. Draw a circuit for complete circuit for 4:1 multiplex. Can you do that quickly? Do it. Do that quickly. You got the idea, right? So you just need to select a line, isn't it? Select the input line based on what combination you choose for the selection line. These selection lines, S0, S1, and so on. Draw some circuit for 4:1 multiplexer.
You have to take here two selection lines, yeah?
You didn't understand the concept? It may happen that when you're receiving someone, other phones sitting with them, if you don't use it, okay, we are considering that one. It may happen that your user data from the other end first may be sent to them. So there are like such eight such processes. Now, but to receive data from two first, I think one. We receive data from two for n first, and for n. Let's say this from only two persons and it is one. One solution. Say for example, you have eight such steps, 8 inputs. You need to receive songs from eight samples, eight songs from different persons. How many solutions have you used? You can't receive data at a time. That's what the condition is. Is that okay? Realization 4:1 cube. Drawing. जब तक ये ड्रॉ नहीं होती आगे नहीं जाऊंगा what is considered? Okay, I'll repeat those who didn't understand this. I'll repeat. Okay, those who didn't get it. Okay, others can continue with the expression. Those who are done with 4:1 go for 8:1 multiplex. Okay, those who didn't understand, just concentrate here. See, share it पता है, ब्लूटूथ पता है, उसमें क्या होता है कि लेट्स से आपके बहुत सारे फ्रेंड्स हैं और सबसे मुझे गाने लेने, लेट्स से दो दोस्त हैं, ठीक है, you have two of your friends, you need to receive a data from two of them, both of them you need to receive the data. But have you ever seen that you have been connected to both of them at a time and at a time you are getting the data? That doesn't happen. Okay, you need to select from which friend you need to receive the data. In share it, you need to select that icon, you know, whatever you, the emoticon you get, उस पर select करने के बाद वहीं से receive होगा, किसी और से रिसीव नहीं होगा. मतलब इसका मतलब ये नहीं कि वो दूसरा सेंड ना कर रहा हो, दूसरा बंदा सेंड कर भी रहा हो तो उसको एरर मिलेगा कि भाई ये कनेक्टेड नहीं. ओके, सो दैट काइंड ऑफ ऑपरेशन इज कॉल्ड एज मल्टीप्लेक्सिंग ऑपरेशन. You need to, you are sending the data from, you know, you are receiving the data from only one person at a time. So how now when we are selecting in the share it, when we are selecting that icon, we are enabling that. That enabling operation can be done using the selection lines. Okay. Now the selection lines. Now what are the minimum number of lines required so as to share data from two persons? Now we are dealing with the, you know, digital circuit. For 0, I may say that you give me data. For 1, I can say that you give me data. The other person. Say for example, you have 8 such friends. Can you tell me how many selection lines you require? Now we have for, you know, for 8 such, 3 bits are, you know, sufficient to, you know, have those combinations such that I can receive the data from all 8 of them. Say for 000, I will receive the data from the 0th person. 001, I will receive the data from the first person, and so on. Whatever may be the other persons be doing, okay, whatever they may be doing, okay, I'll receive the data from the first person, second person, based on what the selection has been made. Okay, being selected a line doesn't mean that the other persons can do what they want. They can always send it, but I won't choose them. Okay, I won't choose that data unless and otherwise the selection line has been assigned to that, you know, receiver or that source. Is that okay? Now what I'm saying is, here you have 4 such friends. Okay, that means 4 inputs will be required. That means what is the selection line required? That two lines are sufficient, right? I may say that for 00, first person receive the data, I will receive the data from the first person, and so on. That doesn't mean that, you know, when you are, you know, receiving the data from the first person, the other couldn't send. Other may send, but that will fail because that is not connected to the other. That is not connected to the receiver. Same thing is happening here, right? See here, I'm receiving the data from a Hindi song from a person. Okay, whenever this S is 0, doesn't matter if this is sending or not. Okay, because if this is 1, okay, it is, even if it is 0 or 1, I'll simply receive whatever from the H is transmitted. Go for that expression, okay, the previous expression. Move clear from that expression. See here, if I need to receive a data from for Hindi song, I'll make this as 0, S as 0. That means what? S 0 हो गया तो क्या मतलब, this term is 1, S bar है ना, ये 1 हो गया मतलब H may be 0 or 1, you will get it here. Isn't it? Because this is 1. Or doesn't matter. Or it may be 0 or 1, it's always going to be 1. Same with this one. Okay. Now is it clear? Go for 4:1 multiplexer. Okay, only one person has done that. Go for 8:1 multiplexer. Do that quickly. Selection lines are simply doing the adding of tree. That's why the concept. Okay, I've given the concept. Those are not inputs. Okay, don't confuse them with the inputs. Those are not inputs. Those are this one. They will simply make the corresponding AND gates, okay, as zeros and ones. They will simply activate one of these AND gates at a time. Okay, so selection lines are simply there to activate. Now see here. See the previous expression. This one, the selection lines is simply activating Hindi or Telugu. It is activating Hindi, it will transfer data from Hindi. Here it is selecting or activating Telugu. So the selection lines are not input, but you know, the activators or activating variables. Okay, so that, you know, the data can be received from only one person. It doesn't matter the other is transmitting. Don't confuse the selection lines with the input. Okay, they are the selection variables or activating variables. Yes.
bit lower to bit lower and 0 to 1 takes that's why zero zero. Because all the combinations of for zero zero only one is there. Each of them are having same word, right? That's zero, that's one. Okay. Which and circuit actually when you circuit and again you have ABC. Now 4 inputs, right? Each of them are having you should be able to realize the expression. Right? Right? How come it will be saying how many inputs are there? How many relation lines are there? It is a scale that the only one is the scale version of this one. Yes. Okay, so this is a 2:1 multiplexer, right? Isn't it? Because here the inputs are only 2. You can do that, but you want to you have to receive the result. Only one person is receiving the result. Multiplexer is a device which is having only one output. You can't have two outputs, right? You can do that, yes. You can do this. We boil down to the same circuit. Do that. You do that. You're right. You can do that. So here has been 4:1. That's flat. But I don't want that. Just the 4:1. You don't selection lines and inputs. Okay, inputs are different, selection lines are different. Okay, four different sounds, four different languages. Yeah, very good. So you should get the crux.
The crux of this. What is the crux of this? Multiplexer is the AND gate. Okay, you select this AND gate based on the selection lines. See here, observe it very carefully. The line you need to select, activate the selection lines as one. Okay, you need to select this Telugu song. Make sure that this will always get, the other inputs always get 1. Then this is definitely going to get transposed. You say this, if one of the input is 1, okay, you always going to replicate that. The other input. This is the AND gate, right? The crux of the multiplexer is the AND gate. Okay, if you make sure that all of the other inputs, rest of the inputs, okay, are 1, that means that multiplexer is selected. Okay, that line is selected. Okay, if you need to transfer a data from a line, make sure that, okay, that the other inputs, okay, you're giving it to the AND gate, all are 1s. Okay, so it depends on how you select these AND gates. Okay, for 0 0 I will select this AND gate, and for 1 I will select this AND gate, and so on. See here, S is 0, it is anyway inverting and making this 1. That's why H is getting selected. When S is 1, this is gone, because and the output will get 1, 0 here. Here we get 1. That's why. So for 4:1, how would be the circuit? 4:1, how would be the circuit? You have 4 inputs, right? So let me draw them. 4 inputs, A, B, C, D. And 2 selection lines, isn't it? How many AND gates you will require? You tell me. Huh? 4 AND gates? Yeah. Say I need to select this. Okay, I'll take that same one. It's Hindi, Telugu, English, Marathi. Okay, 4 songs. Now you need to select this Hindi, right? Make sure that all of them get this may be possibility for 0 0. This may there are only 2 selection lines there, right? S1 and S0, right? I may select this H based on both of them at zeros, right? So I'll take a 0 and 0 there. Simply transfer this, right? And so on. You replicate this. At the end, you will require an OR. Here it will be all ones. I mean, you will be selecting data from here, and this will be 1 1, right? Is that okay? समझा? नहीं समझा? अच्छा देखो. 3 inputs. There are 3 inputs. There are 4 inputs, right? AND gate may take any input. Okay. Don't worry about the inputs of AND gate. AND gates are available with 2 inputs, 3 inputs. If you require multiple inputs, okay, you may cascade 2 of the AND gates. Okay, 2 AND gates of 2 inputs. You will get a 3 input AND gate. That doesn't matter. Okay, that is okay. Inputs means the total. I'm not asking you the input of the AND gate. Okay. Okay, that has nothing to do with the multiplexer. 2 to the power n is to 1. That means 2 power n is the actual inputs. Okay, actual inputs, not these inputs. Don't get confused. So say for example, Hindi has to be transferred, okay, when based on S0 and S1, right? S1 and S0, okay. You have all the 16 combinations of HTEM. Is that okay? What I'm saying is for S1 and S0 as 00, you have all the 16 combinations of HTEM, isn't it? Whatever will the combination of TEM, I just need to transfer H there, right? So I'll make sure that these two are this will be connected, and both of them gets, the others will be as ones, and so on. What is the next one? This will be 1 1. दूसरे कैसे रहेंगे? ऐसे रहेंगे ना, देखो. Here it will be, which we need to select T, right? You need to select it when it is 0 1, right? So it is 0 here, so I'll put an inverter and 1. Is that okay? Similarly here, you need to select this one, right? Based on 1 0, right? So I'll put an inverter here. So all 4 of them are getting selected based on the selection lines. Is it okay? Is it okay? Whose class is there next? No class? Okay, I'll continue. Now, in such a fashion, you can go for 2 to the power n is to 1 multiplexers and so on, right? Now, these multiplexers are having some. Let me stop and start again.